This one?
And this one also, we can just, hopefully that should be fine. Okay,
Does that work? Can people hear now?
yeah, I think,
Yeah, we can hear you now.
okay, Matthew, we can hear.
Okay, maybe we just start now then. Okay, thanks everybody for coming. I'm really happy to have Neill Campbell here, with say a friend of the GP community.
Only half talking about GPs today. I lose my card.
So he's a Royal Society Industry Fellow and a Professor of Visual Computing and Machine Learning in the Department of Computer Science at the University of Bath. But he's moving, okay, he's not. So, yeah, he's going to talk about his work on generative models for inverse problems.
Cool. Thank you very much, Richard. And yeah, so this is a mixture of things that so I spend my time doing lots of living in the interim between different communities, which is fun but also stressful. And so part of it is looking at some computer vision imaging kind of things. And because it's your audience, I'm also talk a bit later on about some GP stuff, which you might have seen before, but it's nice to talk about. Let me just check that this is working. Very good. So I always draw this now because there's deep learning involved in the talk, so we're into the quagmire or things like that, because you can't talk about imaging without it now. But I'll skip over that part. Oh, my little click of magic. It's not clicking. I'll just do this. So there's because it was awards season recently, and I loved Oppenheimer. Has everyone seen? Oh, you can't really spoil it. Hopefully for people. So I don't know if you know. So there's hopefully everyone recognizes the person in the middle. There's that soft hat, and we all know this is Oppenheimer, which is classic hat on the edge. Does anyone know who the person on the left is? And this is a meeting with them. Very good, very good. So that's good. So it's a meeting, and they're walking in the woods at Princeton, and it was good. And I was asked to give a talk on for the AI, the wider sort of AI series at Bath, and I was asked to give a talk about free lunch theorem. And we'd just gone and seen the Oppenheimer film, and I was chatting to a friend of mine from the sort of numerical foundations of mathematics of computing, which is a good thing to talk about in somewhere like Manchester. And he was saying it's really interesting in mathematics because Gödel obviously has the incompleteness theorem. It's quite a fundamental and profound statement to be made, but lots of people within that community go around sort of, no one takes issue with the incompleteness theorem, no one takes issue with the proof of it. Everyone says, no, this is a great thing, we all believe it. And then they go, but I've also come up with a series of axioms that I think you'll find are slightly better than, and it's kind of like, so they still engage in activities that, despite not disagreeing with it, they still engage in activities that kind of seek to, as if it didn't really. And I kind of feel that's always true about the no free lunch theorem. So no one really disagrees with the premise of it or anything like that, but we still engage in activities that are slightly at odds with rather than accepting and embracing the conclusion that this leads to, and that actually that there could be lots of, like the Gödel's incompleteness isn't actually as limiting a thing, it's actually quite a beautiful thing. And anyway, the game you have to play now is to come back in 20 years' time and decide who has had a bigger impact on the world, like someone who is like an architect of a nuclear bomb, someone with general relativity, quite a profound statement, or is actually, maybe the argument is that in the fullness of time, maybe Gödel's incompleteness theorem is a more fundamental statement. But anyway, then we all joke and we all have that. I have to put these memes in now for the students, but this kind of idea that there is one way now, and things like that is slightly at odds with the no free lunch theorem. And so I think this is a kind of interesting thing to talk about. Anyway, that's an aside. So the story time for the first part today is that when we look at machine learning in images, it's about, the first part is really about a likelihood function. So the idea is there's lots of people talk about uncertainties and things like that, but we always use models in imaging that assume independence across pixels and things like that. We just say, oh, images are a very high dimensional object, and so I just deal with them like this, it's fine. And there's like two different things going on. There's images are tricky because it's high dimensional. So high dimensions, yes, there is a trickiness there, but it's not. But also images are awful because they're images and you can't write down a likelihood function. It would be perfectly possible to have a high dimensional construct with a very well-known likelihood function that wouldn't be very hard to deal with. It's just computationally expensive maybe, but images are different because you can't write down a likelihood function that matches with your perception. Like you can't just say it's a Gaussian noise is what you see. We know kind of that's not true, but despite that, we all build all these massive deep learning models and things like that that operate under that assumption. So that's kind of like the premise of what to do today. And as a motivating thing, I've worked for a long time in unsupervised learning. There's a very good friend of Ritsos, Carl Henrik, who we've been working on for a while with this. And I always start them talking about it. Is it actually a thing? And so now you can go and use these crazy generative models, and you can type in the manifold of cats, and you get an image like that. But it's this kind of idea of what is unsupervised learning, and is it actually a thing? So really, you're just saying, oh, find me some function of some z, and I want a distribution over z such that when you do this, you get me back x, and I've used this modern notation instead of x's and y's and x's and z's, but this is just some data. So you get some images or something like that, and I want this back again. And really, that's a kind of crazy statement. It isn't really a thing at all, I would argue, because it has very trivial solutions. And without constraints on this problem, it's a very strange thing to ask for. Like if I can just give you the identity function or something like that, like you give me some images and I give them back to you and you go, ah, that's great, those look like reconstruct very well. You give me some test images I've never seen before, I give them straight back to you and you go, ah, you've reconstructed my test images really well, or something like that. So it's not quite as simple as doing kind of that. But in our sort of higher framework and things like that, think of these things as priors. So if you think of them as, if you think of a generative model as capturing a density that you're going to use as a prior in some further operation, then I think it clarifies a purpose, not necessarily the only purpose, but it clarifies the purpose a bit more of these generative models. And then what I kind of want to talk today about is some of these sort of classic inverse problems things. So these are typical in medical imaging and things like that. So you may have heard of them. So you have some kind of setup where you observe your y. So your y is what you're going to measure, you observe. You have some forward model of the process A. We could assume it's linear, because often it is, but or a good approximation is something like an MRI machine or a CT X-ray scanner. And then X is the kind of thing you're actually interested in. So X might be your actual slice through your body of what's actually there. You actually see by doing some CT scan or some MRI scan, you actually observe Y, and there's some noise in the process. And then what they would call a variation regularization framework, which is not quite the same as variation inference, is just that you would have some data term and some regularizer. And so you would say the data fitting term is going to say, I'm going to try and find an X such that when I push it through my forward model, it matches with the observations Y, and then this will be ill-posed by constructing, so I'll need some regularity conditions on X to try and make it there. And if you're a mathematician, you'll want something like uniqueness as the most important thing, and if you're us, you kind of want to be probabilistically, you want to give me all the plausible things. But then you can kind of see that this very easily maps to a map framework or something like that. So if I said, oh, well, the regularizer is related to my prior, then that kind of makes sense. And if my data term here is related to my likelihood, then all of a sudden I have a map estimate framework or something like that. So very easy to see how inverse problem setups kind of really parallel to map Bayesian problems very, very straightforwardly. And so this only means something if you live in the field of inverse problems, but today we're talking about something in the middle. So the kind of idea is that we're going to look at lots of unsupervised data in the sense of I'm going to look at some reconstructed of things that I like and see if I can use that to regularize a large number of forward models. So one thing you could do is you could get a load of supervised data. So you could say, here's a load of CT scan results, and here's the actual thing after doing a very expensive solve. Can I learn a mapping between the two? But we're not going to look at that today. So onto these sort of modern generative models, and you have this generative model zoo, which I'm sure you're kind of like know all about all these things now. You have these variable autoencoders, generative adversarial networks, normalizing flows and diffusion models and things like that. So these are the ones that was what was generating the image of a cat earlier on. And I've kind of done them slightly separately in that you, like here for the VAE and things like that, you do have this idea of a latent space. So you have this said space. In something like a diffusion model, it's kind of different. as to what the latent space is, because you're kind of like taking a noise distribution actually and modeling it through. So your kind of latent structure is actually somewhere in the middle of the model. And these things seem slightly subtle, but I think actually have an important statement to make upon if you actually want to use some of these models. Where the latent structure is kind of important, because that's what we're going to collapse over to be our prior. So I think people have unreasonable expectations of generative models. So if I take something very simple, so this would be something like a VAE, but it could be anything. It could be a GPLVM with back constraints or something like that, which is a dotted line. You've just got some latent Z and it generates the X. And for a process, you might even say that I'm going to limit the dimensionality, so Z is a lower dimensionality and X is a high dimensionality or something like that. So I'm looking at this image has, it's a 2 megapixel image, so there's 2 million numbers or something like that coming in here. And then you say, how many degrees of freedom are there in the image? And we say, oh, it's obvious, it's a face, so it must be low dimensional, so I could give you like 10 numbers in Z, and I can definitely generate this image. Is that true? How many degrees of freedom are there? Like if you want a really high quality image, you want to get every single hair in my head in the right place. Is it really 10-dimensional images, or actually there's a massively high dimensional object? And now it's kind of tricky because like my identity, the identity of a person might be encoded by a smaller number of dimensions, but you just gave me an image. How am I meant to know which part you want? And we always show, all these models always train on faces because you're lucky, because they all have a bias to low dimensional filtering effectively. And faces just happen to be recognizable from low dimensional features, like the high dimension, like the high texture filtering on your face is not necessarily linked highly with identity. So if I want to recognize who you are, and I take my glasses up, I can still recognize most of you in the room or something like that, even though you become very blurry to me. But you then say, oh, I don't like VAEs because they don't generate these super high fidelity beautiful images, so I use a diffusion model because I get something like, and this is a synthetic image being generated or something like that. And but it's got these too many degrees of freedom, so it's not quite as clear in this construct. And I think we have these unreasonable expectations. People say, I can't use a GAN because it doesn't generate high resolution imagery, but what you asked it to do was not possible. Given the model, you asked it to give you 10 numbers and then to give out something with a far higher set of degrees of freedom. So you kind of also then have to think about what you use your generative model for as to what would be the most appropriate. So I kind of like say, if I list some properties on the left, you might want to say, oh, I need to span the data space. If I'm going to use this as a prior for reconstruction, and as I move around my latent space, I need to be able to produce all the things that I want to reconstruct. The samples that I draw might need to be representative in some settings. So I do want these, I might want a high quality sample, I might not want a high quality sample, I might want to have a condition on the mapping. So if I'm going to say optimize or something in the latent space as I move around, then I need that optimization to be tractable. So I need it to be smooth mapping, otherwise it's very hard to optimize. I might want to be able to evaluate density. So if you're doing this as a prior or something like that, you need to be able to weight the reconstructions by their likelihood. And of course, we're all Bayesian, so we like to account for some uncertainties. That if we fail to model something, or if I'm often in a sort of like a sparse region or an unknown region, I would like to account for that. And then this final thing, which I don't know, it's in some ways it's almost always you feel it's a given, but it's not actually a given. You feel that introspection should be a given of generative models, like because you can generate, you should always be able to show part of your working. So one of the reasons I like to use them is that if you're doing something like medical imaging and you want to convince someone that you've learned something, you can generate an image to kind of show people why you think something is the case. But there's also the kind of like, if you want to be able to play with it and to demonstrate some things, that requires some properties. Like if I move around, say, in this noise distribution, it's not a very clear mapping to the image that I get out here. So then you argue, well, even though these are very representative samples, perhaps, it's not very easy to introspect what's going on in this process. So this is a model that we used quite a while ago, but now we've been using it for a number of things since. And I'm not very good at naming things, and I didn't come up with a name, so I'm not really sure why we called it that. But it's been cool coupled by my collaborators. But it basically, if we started with something like a standard VAE, it's quite boring, and you'd say, this VA doesn't work very well because I take an image And it's obviously a face image for reasons I just told you, so that things only work on faces. So I take you a face image or something like that, and I put it through here, and then you get a blurry output. I'm sorry, the screen's a bit strange, but hopefully you can see that that's a blurry version of that. And you say, I don't like VAEs because they make blurry outputs, so I can't use them because I want my super high resolution. Super high resolution. But I would say, but you're fitting a model. So it's a likelihood thing, you're fitting a model and a likelihood to this. And so what you've shown me is just the mean output. What you're actually doing is you fit a distribution. You have a distribution of your output, and it has usually a diagonal noise term that's associated with this. So this is the standard deviation or the variance of each pixel associated with that prediction. And then what we're saying is that if I got this process correct and I fit my model well, then the thing that you put in should be likely under this likelihood. So if I took a sample of this from this, I should get something that looks like the thing that I put in. Oops, keep tripping over this thing up the time over there. But the problem is that if you look at this, you find out the statistics of this do not match. So I would argue that the statistics here do not match because you've taken something and you've added independent. The sort of like the errors that you've added are independent. We've already kind of thrown away the thing early on by saying images don't have this independence property. So the one thing we do know about images is they're spatially correlated locally. There's no real reason to suspect that a pixel all the way over there is desperately correlated to a pixel down here, but a pixel next to each other should have some correlation. And that's kind of the basic thing we can say about images we've known for a long time. That's how compression works in JPEG and all these things. But we've thrown it away here. And so perhaps we could do something different, and we could say, if we said, instead, let me predict a covariance matrix here that does allow for correlations between the pixels. So if we just go with that, and I predict something like this seems a bit weird, but all of a sudden you start to see that I've got a low frequency reconstruction here, and the high frequencies that I failed to reconstruct them because you didn't give me enough values in here. You only gave me 10 values or something in here, so I can't reconstruct the location of every strand of hair. But what I can say is where hair should exist in the image. I could say, well, vertical frequency should exist here, but not in the middle of your head. You can have them to the side. Oh, there's some vertical frequencies and this white blob in the middle, they might be teeth. And then you can say, if I draw a sample from that, then that sample won't be exactly that image, but the statistics will be represented. So the statistics will match so that the original image is likely under this model and is much more likely than the independent one, because if I keep sampling from the model with independent noise, there's no way I'm going to capture this correlation. And so you can kind of see that same structure by if I take the residual between my mean reconstruction and the input, this is what I have failed to model because of my assumptions in here being incorrect. I gave you two degrees of freedom, so I failed to model it. So I'm left with some residual in the middle, and that residual is likely under my covariance estimate. So this all seems wonderful, and maybe I'm a good salesperson, so you buy all of this and you say, I'll take 20, please. But part of the problem is I just said, oh, full covariance, and that was awful because the image was like 2 million values. So a full covariance matrix is a 2 million by 2 million matrix. So that's not desperately great. And then the only other trick that's coming in here is saying, well, what we could do is we could flip things around, and it's a simple idea effectively from Markov random fields and things like that of saying, if you look in the precision domain, so if I look at the inverse of the covariance matrix into the precision domain, then I could say, I could put local structure in there. So I could locally connect up my precision matrix. And then when I inverted that process, I would have long range structure being captured in there. And in fact, one of the things that we do you've also got constraints when you predict a precision matrix to be positive definite. So I can do this by capturing the Cholesky decomposition. So I take the Cholesky decomposition of the precision matrix. If I multiply that up and inverted it, I would get my covariance matrix. And I could do this really sparsely. So I'm just going to predict 4 extra numbers, say. So I have the diagonal term, which I constrain to be positive. That would be my normal one. I then just predict sort of a lower. If you do this in images like that, you get a lower, that's effectively making sure I get the lower band of it. So I don't predict the sparsity one, I just need to do 4 numbers, and I get the Cholesky factor. When I multiply the Cholesky factor with its transpose, I get this is my sparse precision matrix. So everywhere there's purple, there's a value, the rest of it is white, that means it's 0. And when I invert that, I will get a dense covariance matrix that is constructed from this local prior. And actually, it's not just, whilst it is a convenience to try and reduce the number of degrees of freedom down to something tractable, it's also a kind of a sensible prior, if you think about it, because I said before, like the local structures are what give correlation in images, and global structures are dangerous to predict or tricky to predict. So there's a white pixel over there because that corner of the wall. Now it does so happen that the white pixel down there is correlated with it, because it's all part of the same wall, but there's a white pixel here on this board which isn't in the same plane. And so the white pixels locally, I should be much more confident they are related to the same thing than white pixels that are far apart from one another. So I could build up this correlation by saying, oh, that wall does correlate with here because there's a pathway all along the wall that leads to it joining. If I do something with there's an occluder either side, then I'm less confident, so I have broken the connection. But hey, what are you going to do? We still have to make it tractable, so it's kind of a sensible prior, I think. And this is just to say that you can do this very efficiently, because you kind of think of these as local filters and stuff like that, and that's all you're in deep learning and convolutional networks and all these kind of things. That's what your deep graphics card is doing with all these local convolutions. So I could do this very efficiently on a GPU. I could do something like that. And then if you do this, then you sort of say for these 2 different inputs, this is the mean reconstruction, and then these are just random draws from this. And so there's a degree of variation across here with what you failed to capture, but I would argue that statistically speaking, these images are very close to the statistics of this. So every single sample here, for example, the hair is slightly in a different place, but there are no strong vertical frequencies in the middle of your forehead where there shouldn't be. There are strong vertical frequencies at the edges of the image where your hair should be. And kind of if you look at this is kind of like this introspection part of it. So if I go in and I look at this pixel here, then these are the numbers I predicted for it. So I remember I just predicted the mean, I predicted 4 more numbers, so I only had to predict 5, so that's like O to n, I only had to predict 5 more numbers in there. That was my lower one. If I do this, this is the local part of the precision. But when I invert that, and I look at the row of the covariance matrix corresponding to that pixel, this is that row. And this shows you the correlations that have been captured by the model in that structure. So you can see actually long-range correlations have now been captured. So this is a whole strand of hair is being captured by that, by locally saying, oh, this is what I expect to see. And that's where you see that structure coming through. So even though I only predicted sort of, instead of 1 number, I predicted 5 numbers, I can still use that to capture long-range correlations without having to go density, which I think is quite cool. And so there's obviously links here to the sort of conditional random fields is what we used to use in the days before deep learning. There's lots of vision people spend lots of time doing all of these things. They're sort of adaptive, it's considered like adaptive local regularization, and sort of building adaptive regularizers. It's obviously linked to wavelets as well, because frequency decompositions of images are related to sort of like local Fourier transforms or local frequency decompositions, which can be looked at as wavelets. And there's some things to be careful about that I kind of glossed over, which is like when you take a Cholesky structure of a sparse precision matrix, when you take it actually matters the order in which you unfurl things. If you think about how you know about how the Cholesky algorithm runs, you could kind of think the Cholesky fact, if I collapse an image to a vector row-wise or column-wise, I will actually get a different Cholesky structure. So it's not kind of invariant in slightly the same way. And so we're still working on nice ways to put the priors in. Like you can't just use, say, a gamma prior or something like that over that, because as you go down the image, the statistics should change. So you have to use a modified prior. And you need to bound things, because it's like with all things where you're predicting a normal distribution, there's an element of maximum light year in here. If you're not careful, I could be incredibly precise, and there'll be infinities with appearance. So you need to bound things from below and things like that when you're doing the optimization. But I could do a test for something like this. And one way I could test this model is to say, so we haven't trained here to do any denoising. This has just been trained as an unsupervised model, and now I'm going to use it to solve an inverse problem, for example, denoising. And so I could take a noisy image I put it into here, I have my mean reconstruction, but I also predict my covariance matrix. And then by subtracting the mean reconstruction from the input, I get the noisy residual. I'm sorry, again, it's a bit hard to see on the screen, but most of these high frequencies all over the place are the noise that have been added to the image. But some of these high frequencies are actually structure that's to do with things that, like in general, denoising is just blurring. Because you just remove all high frequencies, but there are high frequencies that you want. And so what I could do is I could project this noisy residual into the space of my covariance matrix, and then I would get something like this, which is trying to say, you shouldn't have lots of high frequency information on your cheek, say, but you can have it in your hair, you can have it around your mouth. And so I then project that, I remove those, and I can add these parts back. And then I get this as the denoised image, and the idea is that I should be selecting which of the high frequencies I want. So I want lots of high frequencies in your hair, but not otherwise. And so if I do this and I train it against something like an actual denoising autoencoder, like a model that's been trained with lots and lots of data to do this task, it still does a better job because a denoising model that's been trained is still trying to encode these independencies between pixels. And you can't reject noise with correlation structure if you don't capture the correlation structure. So in order to remove independent noise, you have to have correlation structure. And so if we do this, you get sort of much better. So this is like the denoising results have removed most of the noise, but they've done it by overly smoothing the image. And I feel that we've still got some quite good structure here. And so now I could take this model, and instead of showing it on images of faces, I could do something useful with it, and I could try and use this as a prior for inverse problems. So going back to the thing I presented at the start, I could say, okay, so I'm gonna set up a model here where I had, if you remember before, my y is the observation that I have, x is going to be the image I'm trying to predict, and now I've got a generative model in the middle here that says from some latent space I can give you likelihoods over images x, and then I have some prior over the latent space z of where I should go in latent space to generate images. And I'm very sorry, we're taking a math estimate, boo. We should really be trying to marginalize out here, but let's walk before we can run, sorry. And then this maps really nicely to that variational framework we had before. So I can say my prior on Z is very simple, because it comes from a unit Gaussian, then it's just a sort of simple, if I convert this into the log domain, it's a very simple model here. And then my data fitting term is now the kind of likelihood model that we had before. So we say like, the noise in the reconstruction process is still Gaussian, so that's fine because maybe with the CT scan you do actually get Gaussian noise. But my regularizer is now the log of the normal end of this Gaussian likelihood. So instead of an L2 term here, I've sort of written like this. This is the like Mann-Lobis distance, like a norm regularized by my covariance structure that I had before. So when I talked about projecting in the covariance, that's what I mean. And I have a penalty term as well here, which is on the loss of term into the matrix. So all of that is just from the log of the Gaussian likelihood. And remember, this is a good thing, is the network is still outputting like a linear in the number of pixels, number of values, even though otherwise, if we were doing this densely, it would be quadratic, but we're still doing linear. So we can do this so efficiently. And so I can evaluate all of these terms without having to invert the matrix, because I evaluate this term if the norm is calculated in the space of the precision. So I can use that sparse matrix multiply that I had before. And so a way of thinking about this is kind of thinking about, this is like a manifold type cartoon. So what we've got here is my green space is my latent space Z. And so we say, as I pick a point in Z, I'm meant to be doing some manifold in the space of images. So the blue axes are meant to be the space of images, X. And so I pick a point here, I'm tracing out some manifold space in the space of images. I've kind of like colored them green to gray. There is a distribution as well on here. So the more likely you are in your latent space, the darker the green here. And then I'm kind of saying, all my images. So in this case, let's pretend that I'm looking at MRI scans of people's knees. So I say I've done a data set across there. All of the images of people's knees should live somewhere on here. So that's kind of what this model is saying. But in reality, they don't. And you know that because when I reconstruct with the BAE, I said I got blurry reconstructions. So blurry versions of knees live along this line. The real images of knees live slightly off this manifold. And the kind of difference is that if you use like this your simple L2 sum of squares loss or something like that to do this process, what you're saying is I can extend this manifold to the entire image domain. I do it just by putting like a Gaussian blob at every location. But the thing is, we know that does extend to where these images are, but we know all around them are bad images because we just showed, like I showed you at the start, if I just add independent noise to all these pixels, I get all these bad images in between. Whereas a better model for what the actual image statistics look like is something like this. So you say, as I go off the manifold, they should have very spiky Gaussians. So they're saying there should be quite complicated correlation structures they capture here. And so my nice clean image lives somewhere on the spiky thing from here. But all around it, there's lots of space that is close to the manifold in a Euclidean distance, but isn't close to the manifold in a projected distance. Is that kind of difficult cartoon to get, but does that kind of make sense? And then there's I had a very astute comment from Simon Harridge at UCL. It's like, shouldn't they be like this? And like, really, to be efficient, you should have all these spiky things coming off orthogonally to the manifold. And in an ideal world, they would be like this. If the optimization went really well, and you think about it, that would be like you'd basically be having little springs for all of these things, and you would do that. But that relies on you're sort of like doing some crazy deep learning thing with gradient descent from actually doing a really, really good job, which it may not do. So if it doesn't do a really good job, they might look like this, but ideally they would look like something like that. So as a like demonstration of a sort of proof of concept of this, I'm just going to take something with there's a fast MRI data set that looks at these knees or something like that. And the idea is here, you have a number of spokes. I don't know if everyone knows how an MRI machine works, but you have it's sort of all these big magnets go around from different angles. And so the longer you're in every time you hear a big thunk in your MRI machine, it's doing a different angle with moving the magnets around. And so the longer you're in the machine and you're not meant to move between this, the more spokes it can take, so the greater number of sampling angles it has. So that takes a long time, and obviously you have to stay still. If you move during that, you get errors. And so the goal here is to try and reduce the number of spokes you see. So can I get a really good reconstruction with fewer measurements? That would be a win. And then the practicalities of this, we're doing gradient descent in the image space to try and match it under the prior, but also in Z. So I'm going to pick some places in the latent space and try and optimize the latent space to give a good prior over the image as well. And so this is the kind of thing where you can see the difference. So here's a ground truth image or something like that. So here's a mean that our model might give just an unsupervised sense. So you see, yes, I'm producing overly smooth knees because that's what we thought would happen. And then if I subtract one from the other, I'm going to get the residual. If I just had this diagonal covariance, then the weight of the variance is correlated with there, but it's all independent. If I have this structured sample covariance, you can kind of see these shapes, these correlations of edges and stuff like that start appearing in this model as well. So it's the same as with the faces. I'm starting to capture the correlation structure here. And we can do this called introspection thing. So I do the same thing. If I look at this particular pixel and I plot the corresponding row of the covariance matrix, you see this is the kind of thing where it says, in here, there's some boundary layers of the meniscus and the skin's being captured here. Along range or within your knee, there's some cartilage in the middle of your knee. I'm capturing that correlation structure in the model. And that's what I'm going to enforce when I use it as a prior to do the reconstruction. And then there's the cool thing about this plot is kind of saying that I've got two baselines here. So the green dots, what I've just shown you, these two other models are kind of state-of-the-art models for doing reconstruction, but they're trained in that supervised setting with a specific number of spokes. So for example, here, I say I trained a model with, I think 25 angles, and I train it to reconstruct there. So it does a very good job at 25 angles, and then it kind of tails off a bit. I have another model which I trained to reconstruct at 125 angles. So it does a terrible job until you give it 125 angles, and then it does a good job. And the interesting thing is that the model that's unsupervised, it doesn't know about how many angles or anything you're going to do. It just knows about the statistics of the model, kind of as an envelope that does both. So it does the same sort of, you can't do as well. If you give me more spokes, if you give me more angles, I'll do a better job. But I'm kind of like covering the envelope of both of these two models without actually having trained in a supervised setting. And similarly, you could look at it here. This is just noise level. So I could change the number of spokes and I could change the amount of noise in the process. And it's the same kind of story. If I have a model that's trained for a low noise, as you start adding more noise, it really drops off. You can have a model that's more robust because you train it for specific noise. It doesn't do as well there. It sort of peaks here. But again, we're kind of covering the envelope. You've got one model and it doesn't matter. You didn't need to tell me what you were going to do in your reconstruction. I was just going to try and capture statistics. And you can kind of, when I say fail, you can really see it failing. So this is like the supervised model, until it gets the right number, really can't do anything at all. And the idea is that we can do a good job. You sort of, it gets better with time, but you can do a good job irrespective. So that's the kind of story. So there's lots of open challenges. I had to I cheated a bit because I got some data for this project. I got some data and I didn't tell you how I got that. How did I reconstruct the MRIs in the first place? Well, that's clearly cheating. So I had to use an expensive otherwise system. I had to use many scans or something like that to reconstruct it. I've also cheated a bit because we should really be doing this in complex space and stuff with MRIs and things like that. And so there's lots of other things that we're working on to go there. But I think it's a proof of concept of trying to capture this idea of character correlations. I think it's a very interesting one. Very good, but I dropped my Bayesian card along the way because it was all math estimates. So sorry about that. And then to say that to try and scrounge my Bayesian card back, we do organize a workshop now, and it's with Arno Soling as well as one of the organizers. So we've been now in its third instantiation. So we're desperately trying to get uncertainties and stuff like that into the computer vision community. And it's actually the ICCV workshop. It was something like the third largest workshop or something like that. So which we were actually really pleased about. So the message is starting to get across. So lots of people in the imaging community are now starting to consider like uncertainties in there. So this is a positive thing. So if you work in uncertainty, but you don't work with images, go talk to your imaging and computer vision colleagues and try and get them to spread the good word and come along to the workshop and things like that. That would be great. So it extends to non-Gaussian likelihoods, but I was going to skip. Oh yeah, sorry.
So because in this community of generative models, they have very specific metrics to measure the quality of the generated image. So you said that your statistics sort of match when you take into account the dependencies in the covariance. How do you measure that match?
So I measure it as a kind of actual statistics. So I measure like the likelihood. So like saying I have predicted a likelihood, so I measure the likelihood of the image under that, like the negative log likelihood, whatever you want, the log likelihood model. The problem with sort of like all these like Fresnel scores and things like that is, well, what troubles me is you kind of, it's not a stick thing, it's an observation thing. So one way people say, oh, the perceptual loss or something like that is, I take a discriminative model, a really big discriminative model like ResNet, a big ResNet model, and I train it on ImageNet, which has lots of images of dogs in it and things like that. And I say, oh, these features, I cut somewhere near the top of it. I cut off the top and I do a feature map and I just say, oh, the inner product of that feature map with itself is a measure of whether you're doing a good job or not. And I don't know, it might be, but it certainly wasn't constructed to do that. It was constructed to try and predict images of dogs correctly and categorize ImageNet correctly and things like that. And it's a bit tricky. So you can kind of say there is this, it's like emergence in large language models that people talk about. It's a little bit ethereal to me. So I'm not saying it's a bad thing to do, but I'm saying it's a tricky thing. Like that could be horrifically wrong. Like it's probably very good until it isn't good, and then it's very wrong. And so as a perceptual loss on a type of images, so if I train one of these models on that and I say, oh, let's look at MRI images, and you've got a model that's never seen the statistics of MRI images, it's a little bit tricky to know what should happen there. And so this does quite a good job under there, but also like the other metrics they use are kind of objectively bad in the sense of if you take like the mean squared error, we know it's objectively bad because I've just shown you that I could make a model that is very close and very far apart by adding different amounts of independent noise, and that would have exactly the same score under the model. And I kind of feel the subspace in the Fresnel score is the same. I could navigate that subspace by, you could give me a score and I can make an image arbitrarily bad with the same score, if you like. It's kind of what, it's not really constraining the space. So I don't know. Evaluating these things is not, but one of the things I think that I feel very strongly about is that test reconstruction likelihood alone is not a good measure. You cannot, I think with the unsupervised, you can't have it task agnostic. So for example, the way I would evaluate this is a denoising problem. If I say, if I can do a good job denoising, then I'm doing a good job, because part of modeling something is not modeling, is failing to model something else. So if I had the identity mapping and you give me pictures and I just give them back to you, and you say, I give you lots of pictures of faces to train, and I just say, I'm not really doing anything, I just give you the faces back again. And then you say, give me some test faces I've never seen before. Not really okay, I just give them back to you. You go, these reconstruct really well. And then you give me some pictures of giraffes, and I go, just give them back to you. So wait a minute, you shouldn't be able to reconstruct giraffes, because you're meant to only be able to reconstruct faces. And so you can't actually test it. Testing on this, like just the test data coming from faces doesn't really tell you about the model, because if you have some probability mass, you should start. It's kind of like if you test it discriminatively, then it's unbounded. Like you've got to test it against all other things. I'd have to show you that it doesn't reconstruct all things that aren't faces. That's a very hard thing to demonstrate. But if you have some probability mass and you say, in order to do this, I'm going to pull mass from the ether towards, I'm going to pull mass from the distribution of all images towards faces, then by pulling the mass towards this face, inherently I am removing it from somewhere else, because the mass is conserved. So if I pull it towards faces, I must be not able to reconstruct some other things, because I'm putting my discriminative power in somewhere specific. And so that's kind of like where we're going with this. But it's a really good question, and it's still open, and that's the problem, is that if we had a closed form likelihood to evaluate this, then we wouldn't need to do it in the first place, because we just use that likelihood. It's a big problem in imaging, because people then complain, you assess with the goal is to find something that you can't compute that's perfect. So it's like, before SSM was hard to compute, so you'd always evaluate with that, and you say, but if you had a metric that is the true metric, then you should be optimizing for that metric. And so you can't have an independent metric in that way. So I'm going to skip over the non-Gaussian likelihoods, and now because we're in a wonderful, amazing world, I was talking a bit about GPs. Otherwise, I feel like let my host down. So I think most people might have an understanding of the basics around deep GPs, things like that. So I will probably skip the first part of it relatively quickly. But I've been with Carl Henrik and stuff like that. We're spending quite a bit of time on compositional models. So the model you saw before was effectively a 3-layer compositional model for inverse problems. And so I don't like to call these deep models, because it's not quite the same concept. It's like I'm saying, rather than just saying these are very simple things and I can concatenate lots of them, there's the kind of idea that something sensible might be happening in each of these things. So they have specific purposes. So you can see something like this. It's like, this is just an unsupervised one. You say, well, like if these are just completely arbitrary, then why can't I just replace this with one big function? Why do I need 3? And you have models like this where you say, I might have multiple sources I might have sort of some information here, lots of information here, some information here as part of a hierarchy or something like that. It might even be a supervised model with information coming in. I've got 2 sources of information coming in and make some varied predictions. So I would consider these to be compositional models. And what we're trying to think about is how uncertainty is propagated in these compositional models. So a deep GP would be something like this. Or if I supervised it, that would be straightforwardly a deep GP if I said each of those layers has some form of GP prior. And part of the problem, so I think this is why you think of them as deep GPs rather than a deep Bayesian neural network, which has many layers. But I think the results and the logic apply to deep Bayesian neural networks as well, which is why I think it's an important thing to talk about and to think about. And so I'm saying that these models contain compositional uncertainty, and I'm factoring compositional uncertainty as it's not a different type of uncertainty, it's a mixture of things, but I'm using it as a particular phrase. And I could I will in the next slide, it's trying to explain what I mean by that, but it's related to ideas around identifiability from statistics, I would argue. So as an example, you could consider alignment. So this is some more work we used to do, because I do lots of work in graphics as well. If you were trying to align all these different shapes together, you would say, I want to put them in correspondence. So a point in each one does that. And you have this challenge of saying, if I just match things together pairwise, I might not have a consistency problem. So if I match from A to B, from B to C, from C back to A, I should get the identity, but I might not. What you want is some sort of global method of aligning all the information together so that you have some representation here where there's a strict correspondence. So the values in here correspond to the same point everywhere. And you can kind of see in like a construct, if I was doing this as a generative model, say over shapes, I would want this correspondence to occur. So by the time I got to here, I've kind of drawn some Smarties around the thing. All the Smarties should be in correspondence. So the big blue one here should always be at the same intersection. So that is what I mean by something like alignment. And so let's reduce that down to a really simple example and just say, I've got a really stupid problem. So my problem is I want to match, I have some shapes like this, and they have to move shapes like that. And hopefully, if you know a bit about geometry, you know that you just need a rotation and a translation to achieve that goal. But I'm going to make the problem a bit worse. I'm going to say you get two. So you get to rotate and translate, you then get to rotate again and translate again, and then you get the output. So I've introduced some extra steps in this. And now it's a bit interesting because this is under constraint. And my argument is lots of the time in compositional modeling, especially on unsupervised learning, it is going to be under constraint because you've introduced lots of extra dependencies. But I've explicitly made this under constraint. So you kind of see, I could do lots of different types of rotation. I could do lots of different translations, and it's all going to be fine because I can then undo the rotation to the correct one, and I can do that rotation. So I can do this. So there's lots of uncertainty. This is my compositional uncertainty. There's compositional uncertainty in the middle of it that doesn't necessarily appear at the output, but there's a problem here, and hopefully the astute amongst you will have spotted that the problem is that whatever I do here, I have to undo here. So these two things are not independent of one another anymore. So they must talk to each other. This and this must be in cahoots in order to ensure that when I do this, I end up back at modeling my data. And that is the entire argument. That's the entire argument. So if I was doing something like an alignment type task or a non-stationarity task, so I've got a chirp signal here, and this is a simple example of a non-stationary signal. Yes, so the length scale of this is varying across there. So you say I can't just use a stationary GP to model this, so I'll use a two-layer GP. I'll basically warp. I have a first layer that warps the input, and I put that into the second layer. The second layer, the first layer can be stationary. The second layer can be stationary. Their combination together is no longer a stationary GP. And so you start seeing that there's a correlation structure. So if I use the orange warp, then I have some ambiguity in my warping structure here. I can shift my warps to the left or the right, and it's fine as long as in the next layer, orange matches with orange, green matches with green, blue matches with blue, and then all of them line up and agree with the data. But they have to. But if I do orange here and blue here, then it doesn't line up anymore. So there's correlations involved between the two layers. Or you could do something really simple like a sinusoid and just say, I'm going to do again. I'm going to introduce this, making this sort of system that's unidentifiable. I've got unnecessary compositions, and I can switch the things around. So I can actually I don't have to be, I can switch the phase of this as long as I compensate for switching the phase later on and come back. All of these will model the same sine shape. And this is a really stupid thing to do if I just wanted to model a sinusoid, but the argument is most complex structures will have ambiguity in the middle of the layers. And if we're really capturing uncertainty all the way through, we might want to express that uncertainty in the middle, because it does have an effect a bit on the output, but also we might have things that feed off during the middle. Remember that in the diagrams I saw, I think information could come in and leave at any point of the hierarchy. So we want to have uncertainty being correct throughout the hierarchy. And so if you want to do a DTP or something like that, it's all very standard. So you would use a formulation based on, say, a sparse variation of TP or something like that. We have our inducing distribution. So we use inducing points. We use inducing distributions all the way through the hierarchy. And our training goal is to approximate, find the variational parameters given some input and output with these distributions. And then I might skip over the next two. So we were kind of basing this on Hugh's work with Mark and the standard doubly stochastic variational inference is a standard way of doing this. I was going to skip over these slides, but I can give the slides out. So I'm hoping that people kind of know roughly about how it works. But the key part is that by the time you get your decomposition at the end, you have a set of independent So you're approximating distributions over these pseudo outputs are independent. You have one per layer, one set of approximations per layer. And so this is a mean field assumption. Yeah, so the correlation structure in my posterior limb estimating has been broken across the layers. And so here's the problem with it. So I have this mean field assumption so that I have a product of these things. But if I go down to like the stupidest example I can imagine, so you can either be X or minus X. And then if I pick one in this one, in order to model this data, I have to then pick the opposite one in here in order to ensure that my data goes through there. So the kind of like thought process goes, if I assume that all my DGP layers are independent from one another, so the functional form of these layers are independent, then I'm going to have a sort of distribution of outputs of each layer. They form an uncertain input, if you like, to the next layer. So you could say, no, I have a GP, instead of having a fixed X and some fixed Ys, I now have an uncertain X at each layer coming in because I got the stochastic layer before me. And so similar to like the work with Kara's motion and things like that, like there's a whole body of work on GPs with uncertain inputs distributions. You can say I can analyze my each layer's function as some data plus some uncertain, some variance that applies to that, and I could form a linear sort of first order approximation to that. So let's consider a single input X. I can write this as, oh, it's my functional layer plus some uncertainty. And I'm going to say, this is going to be the mean, and this is a some zero mean distribution. So I'm going to expand the distribution and the input around that mean. And if I say it doesn't really matter that they're not Gaussian, I'm just going to say that the marginals of a DGP are not Gaussian in general, but I'm just going to say it denotes some zero mean distribution. So I'm not going to assert that it's Gaussian. So I'm just going to model it by looking at its variance. So let's just consider a very simple setting. And so I have an input to the next layer is the mean of the output of the previous layer, plus some distribution which has a finite variance that's going to go into the next part. And what we want to show is that the variance, what we show is that the variance of this object as you go through the layers increases with increasing variance of this. So if I get variance of this object going up, the variance of the layer, the functional layer, as a result of that will also increase. Therefore, so I will show that to be the case. And if I show that to be the case, then you say, like, if I have any uncertainty in here, as I start concatenating the layers, the variance grows. And if the variance grows, that leaves me with two options. By the time I get to the final layer, I will have lots of uncertainty because the variance is guaranteed to grow. And so if I have lots of uncertainty, I'm going to say that means I'm going to have a poor fit to my data because I'm lots of uncertainty everywhere, not just away from data, but I'll have lots of uncertainty at the data. So that means I can't fit the data. So in order to fit the data well, I can't allow that variance to grow. And the only way to fit the data without the variance growing must then mean that this can't be big. This must be small. In fact, this must go to 0. And so if that goes to 0, it means that all of my previous layers must collapse in their uncertainty to a deterministic function. And this is not because the model says you must collapse to a deterministic function. This is because of the mean field assumption on inferring from that model. So mathematically, it's kind of like relatively straightforward. You just say, well, like, it's fine because I can say the derivative of a GP is also a GP with respect to GP. So I can build up my correlation structure for the covariance like this. And then this is exactly the same as you do with standard uncertain inputs GPs. And then you can say, this is just a linear transform. So I could take a Taylor expanded linear transform. And I say, this is my mean and my variance for the output layer from that particular output from that particular layer. And then you can combine using the law of total variance. And you say the variance in the resulting layer is this term. And then you find that if you look at all these pieces of information, like this must be positive, this must be positive, this must be positive. The only thing that might not be positive is here. So the only term in that expansion that could potentially be negative, as in stochastic variance growing, is this second derivative term, because it's off diagonal, so it would be second derivative off diagonal. And so kind of we show that this is related to where you place your inducing points. So if I just do a thought experiment and I put my inducing points, I say like this is the range of my function, and as I go from left to right, I'm just adding more inducing points. So I'm putting more inducing points where these triangles are. But so in order to have a high value of that second order variance, I must place my inducing points far away from data. And so the argument then comes back to if I try to collapse the variance, the only way I can do that is by pushing my inducing points away from data. But I do not want to do that because I need my inducing points to be close to data in order to model the thing. So again, if I push my inducing points away, I could not cause this variance to continually expand across the layers, but that would mean pushing the inducing points far away from data, which is not what I want. And the more inducing points I put near data, so the data here, this is the red function here is the second order derivative. So in general, the second order derivative collapses to, it becomes less negative and tends towards zero as you increase the number of inducing points where data exists. So does that kind of like all tie together? The argument that collapse together is that this is just mathematical kind of argument of the intuition that we had before that was exactly the same, which is like if you have independent functions between each other, in order to match the data, if you're going to rotate arbitrarily, you have to secretly tell me how you rotate it in order for me to compensate later on. So we must talk to each other. And then you kind of say, well, now, okay, how do you go about fixing this? And this is kind of where you can see the relationship with the first part of the talk entirely, which is this, you could use a precision structure. There's one potential solution is to use the precision structure. So again, if I had a very deep very deep GP, I can't produce a variational distribution across all the inducing points from all the layers, because that would be a very big object to have to deal with. But what I could do is I could do in the precision, I could do neighboring layers. So the indice here is just a layer. So I could say layer 1 can talk to layer 2 can talk to layer 3, and therefore layer 1 can talk to layer 3 because it can pass the information via layer 2 as you go through. And so you kind of have like your sensible ones would just be to build one massive joint distribution, but it's very big. You can do this chain-like factorization to try and save you effort on that. Or you could do another thing that Ivan came up with quite cleverly, which is to say you could use your inducing points as inducing locations. So you could say, I only need to specify inducing points at the input layer, and then I pass those through the structure itself. And then because they are, then if you sort of say, that's like saying you kept a record as you go through the structure, you kept a record of where you were going. So when you went through the first rotation, your inducing points recorded where they rotated to, and they have that information. So later on down there, the function is only specified where it needed to be specified. So this information is being tracked as it goes through, and this is kind of a slightly more efficient methodology. Neither of these are particularly perfect though, because if you do that, you think about it, your distribution over the pseudo point is now quite complicated because you're going through and you've got to carry complicated information. So it kind of works for not too complicated compositional hierarchies, but the more complicated it gets, the more complicated the structure we have to be in here. And you can kind of see the same kind of philosophy here. Like if this has to have a long range link with this, and it's quite a complicated link, then lots of information is having to be transferred through this structure. But you can see this exact thing happening. So this is chirp decomposition again. And if I just use a sort of doubly stochastic variation inference, indeed it does. So you can see these, wherever there's data, these functions completely collapse. And they shouldn't. There should be sort of say ambiguity over here, an ambiguity in this setting. There's not you could imagine there could be really wide ambiguity here. The reason there isn't really wide ambiguity is that we still have priors. So we can constrain the range of that function for priors. And you can get sort of awful thing where we can actually capture, as you saw before with the oranges and blues and greens, you can capture a level of bimodality in this because you can propagate the information along, but you kind of want to constrain a range, otherwise it's unbounded. And so this is one of the things that we do, say, for some heartbeat data or something like that. So we've got these kind of weird constructs that are a bit non-stationary, and we actually constrain this to be monotonic. So I'll talk about that in a second. But if we do that, you see, you collapse. So I'm warping this space to try and make this stationary. this heartbeat, but I collapse to a single instance of it. There's no uncertainty in there. Whereas if we do this here, there's actually a degree of freedom as how you collapse this. And then these signals are all nice and stationary. And when you combine them back together, they both model the data well. But if you see, it's extrapolation kind of argument. Like as you go away from the data, you suddenly do something very strange here. You disappear off to here and disappear off to here. That's because you made a particular choice of the warping function that doesn't really extrapolate very well. Whereas here, there's lots of vagueness in the warping function here. It goes forward, but that's fine because then the vagueness matches to here. So instead of like, so why is this suddenly very confident disappearing off to there when it should just be expanding away from the prior? And over here, you see, oh, that's my error. Sorry, I should have made this a bit bigger. But the error bars are kind of going nicely out here and nicely out here. And there's slightly better uncertainty in this part from it. And so, I don't know, I'm probably running out of time. So I can show you, there's an alignment, there's sort of just a model with that, oh, this is a monotonic flow thing, which we warp the process via an ODE or something like that, and you can't commute things. That's my Ghostbusters reference. You can't cross the streams, so you can't commute. So this is a prior on sort of making a monotonic process to try and do a warp. And if I do that, I get things like this. So if you try and align these signals in a multitask to do multi-output kind of context, you can see that like, oh, I can't really predict. The error bars are kind of a bit dodgy. And then if I do something like this and I predict my uncertainty in the warp, I get sort of very nice error bars in regions where I'm interpolating away because it's the composition, even though it's only two layers, these two layers have to talk to each other in the model. Very good. And I'll probably stop there. Oh, no, I should do an advert first. So we've been doing this, so this is the center that I lead in Bath, that we do a lot of work on motion analysis for people and things like that. We have crazy people like this. I don't know if you've ever seen the skeleton at the Olympics, but there's a skeleton test track. They throw themselves down really steep slopes on tea trays, and we try and build biomechanics models and things based on that. We have a studio like this. These are some force plates that capture gamma reaction forces, and I know you do a lot of work with latent force things. So things I'm interested to talk to you guys about are physics-informed machine learning to be doing with this. So one of the challenges we're trying to do is understand how the human body performs motion, which is how the brain correlates to that. And so in this case, machine learning with very sensible, no free lunch, sensible physical priors will really help us out. So that's something to talk about. But anyway, I shall stop there. I'll leave with the people there. Cool. Thanks very much.
Any question?
Can I just go back to the diagram you said you had about a low manifold with Gaussians sticking out?
Oh, yeah.
So that is technically modelable as a mixture of Gaussian distributions whose means are constrained on a low-dimensional manifold. So that's what mathematically that thing means. So I was wondering
How do I jump back? Sorry, 1 second. Where did we have that? That was probably here, maybe. Yeah.
So this is essentially mathematically equivalent to saying my data is a mixture of Gaussians whose means are constrained on a low-dimensional manifold.
Yeah.
Now, one can parametrically perturb this assumption by adding some noise to the means. So then you're having mixture of Gaussians whose means are not constrained to low-dimensional manifolds. So has anyone done an ablation study that when you do this parametric breaking of the manifold assumption, the convergence of the deep learning model somehow gets affected, gets worse?
Well, this is a bit that makes the whole thing is a bit awkward, because if you kind of look here, you've got this, I drew this diagram just by rotating these, but now it's a bit awkward because I'm saying there's a distribution here which should be orthogonal to this thing, but it's not actually, like, it's a degenerate Gaussian. If it actually is orthogonal, then I should have no variance in the direction of the curvature of the manifold, which is kind of roughly the same thing as your, like, uncertainty in the mean here corresponds to shifting left or right along a particular choice in the manifold.
If you break the manifold assumption here, slowly perturb it away from the manifold assumption.
As in, I make my data move away from the manifold.
The data distribution is no more, the means of the Gaussians are no more a low-dimensional manifold, but you add noise to the means. So then you're breaking the manifold assumption parametrically. In that case, do you see that the deep learning algorithms convergence somehow gets worse parametrically, or is it sensitive to this assumption?
Well, that's effectively, so this is effectively what that denoising experiment is doing. So if you think about it, if I did this with faces, so I had a face that's here or something like that. And then when I'm trying to, if I want to measure my ability in my model to capture this manifold, what I could do is I say, I'd like to learn to project. So if you give me a new image, I'd like to project it onto my manifold. And if I've done well, if you give me test images that are good, they should be close to the manifold. The way I could do that is I could perturb them off the manifold. And what I'm doing by adding Gaussian noise to an image is I'm perturbing it off the manifold effectively. I'm pushing it away. But because I push it away, if I don't push it away too far, there's the kind of thought processes, I should be able to project it back. I now know where it should go. So in general, if you give me an arbitrary face, the problem is I have no idea where on this manifold it should go. So if I want to measure the distance from it, to see whether this assumption is violated, I have no idea where it should be. But what I could do is I could start with something where I know where it should be, I could push it away, and I could see if projecting it onto the manifold pushes it back where it is. So if I push it miles away, then it could project back somewhere else, and I wouldn't know. But if I project it away by a small amount, and I push it back, and I come back to close to where I originally was, I have a reference anchor for where it should end up. And if I do that, that kind of gives me confidence that I'm actually capturing the manifold. And if I could mathematically prove that it was as sensitive to perturbations, I always projected back into here, then I would have a convergence proof that said. So at the moment we don't. So if you're doing, say, an inverse problem, you don't have a uniqueness guarantee. Like you could imagine that you kind of like, you'd want your regularizers normally to be convex in the sense of no matter how I perturb this, I will go back to the same space. But we don't have that. If you push this a bit too far, like if I push something too far here, it could jump over here. So the manifold isn't guaranteed to be stable. Oops, in that sense.
The reason I asked this question is because in our group, we have tried rewriting the deep learning convergence proofs, assuming a manifold assumptions like this. And our feeling has so far been that there's something fundamentally missing in our mathematics at this point. The proofs are entirely blind to the manifold structure. So there is, my gut feeling currently that there is simply no way the deep learning mechanism sees the manifold assumption. Like, or maybe there's something fundamentally missing there. Because the way the deep learning proofs work, they just don't see the manifold assumption.
I think that's true. So I kind of said, but yeah, there's no convergence proof of something like this.
Experimentally, what do we see? It does experimentally, is the runtime sensitive to the manifold assumption being true or not?
I think a better way of looking at it is, well, my personal thing is that what you want to use this in practice is stability under this protection. So if I go here, then it's a bit awful because you sort of move off here and then you kind of definitely should end up going somewhere here. And that feels like everything's a bit awful. Whereas if I have something like this, then I feel that I have stability under that. Like, it's manifold by construction in the sense of, like, as you move around here, you must smoothly move this. If you have a smooth mapping, you must smoothly move along something. It's not a strict subspace or anything like that, but you must smoothly move along something that describes it, and it has a curvature. You can evaluate the curvature of this thing, and you can have continuity conditions on the curvature. So it does have some structure. I guess it's depending on if you what type of convergence you want. It's very elusive, but that's like my friend Simon, who his book now, Understanding Deep Learning. We don't understand deep learning. So I think it's very important to be working on this, but I offer no guarantees of convergence or anything in this sense. We are looking at some of those problems with the inverse problem people. But yeah, I don't have a good intuition as to what. That's why I'd say, like, this would be what we'd like to do. And if I knew that, the answer to your question, I would feel very confident drawing this diagram. But I feel much more confident presenting you with this diagram, saying, like, well, we're trying to get it to be there, but you don't really have any. We don't really have any guarantee. We can't look at the curvature of these things and regularize them. We are trying to do that. We're trying a model where we penalize the curvature on the manifold to try and explicitly make this the outcome. But you train the best we can.
We probably should stop there because Neill has a pipe bar.
Oh yeah, forget to do that.
Thanks so very much.
But thank you very much.